Hello everyone, and welcome back to Tech Adventure. I hope you're doing well and staying focused on growing your skills in software development, interview tips, and embedded systems. In our previous videos, we covered the top 50 real C and C++ interview questions and explored the solid principles. If you missed those, I highly recommend checking them out. They provide a strong foundation for what's coming next. As promised, we're now moving ahead with key topics like design patterns, RTOS, and microcontrollers. Today's focus is on design patterns. Whether you're familiar with them or just getting started, this video will help refresh your knowledge or build a solid base, ideal for both interviews and real-world development. If you find this content helpful, don't forget to like, subscribe, and share to support the channel and help others in their learning journey. Let's dive in. What are design patterns? Why are they important in C++? Design patterns are proven, reusable solutions to common problems that occur in software design. Think of them like blueprints or templates for solving specific issues in object-oriented programming. They're not code you copy-paste, but concepts you adapt to your own problem. Design patterns in C++ are like best practices or standard templates that make your code more efficient, scalable, and maintainable. By using them, you're solving problems the way experienced developers have solved them for decades. What are the different types of design patterns in C++? In C++, design patterns are commonly categorized into three main types, just like in general software engineering. Each type addresses a different aspect of software design. 1. Creational design patterns. These patterns deal with object creation mechanisms, trying to create objects in a manner suitable to the situation. 2. Structural design patterns. These patterns focus on how classes and objects are composed to form larger structures. 3. Behavioral design patterns. These patterns focus on communication between objects and how they interact and delegate responsibilities. There are many design patterns available, but the choice of which pattern to use depends on the specific project requirements and context. In this video, we won't cover all pattern in depth, but we will focus on the most commonly used design patterns in C++ projects. We'll also explore real-world examples to help you understand how and when to apply each one effectively. Can you explain a design pattern you have used in detail? Here we are going to see the top most commonly used design patterns in C++ projects, explained with clear use cases, structure, and simple code examples to help you understand where and how they're used. 1. Singleton pattern. Singleton is a creational design pattern that lets you ensure that a class has only one instance, while providing a global access point to this instance. All implementations of the singleton have these two steps in common. Make the default constructor private to prevent other objects from using the new operator with the singleton class. Create a static creation method that acts as a constructor. Under the hood, this method calls the private constructor to create an object and saves it in a static field. All following calls to this method return the cached object. When you need a single instance to manage application configuration settings, a single logging instance to manage log files, and a single instance to manage cache data, we use the singleton pattern. Singleton pattern ensures controlled access to resources, such as database connections or configuration settings, and guarantees that there is only one instance of a class, maintaining consistent state across the application. 2. Factory design pattern. Factory method is a creational design pattern that provides an interface for creating objects in a superclass, but allows subclasses to alter the type of objects that will be created. Steps to implement factory method pattern. Define an interface or abstract class. This will declare the factory method. Create concrete classes. These will implement the factory method to create specific objects. Imagine that you're creating a logistics management application. The first version of your app can only handle transportation by trucks, so the bulk of your code lives inside the truck class. After a while, your app becomes pretty popular. Each day you receive dozens of requests from sea transportation companies to incorporate sea logistics into the app. At present, most of your code is coupled to the truck class. Adding ships into the app would require making changes to the entire code base. The factory method pattern replaces direct object creation, new, with a method that returns objects. While it still uses new, it's now done inside the factory method, making object creation flexible and easier to override in subclasses. For example, truck and ship both implement the transport interface with a deliver method. Road logistics returns a truck, and sea logistics returns a ship. The client code only relies on the transport interface, not the actual object type, ensuring flexibility and decoupling creation from usage. Use the factory pattern when require encapsulation. The client doesn't know if it's a truck or ship. Scalability. Adding air logistics later is easy. No need to touch client. Flexibility. You can decide transport type at runtime. 3. Adapter pattern. Adapter is a structural design pattern that allows objects with incompatible interfaces to collaborate. It acts as a bridge between two incompatible interfaces. Steps to implement adapter pattern. Create an interface. Define the target interface that the client expects. Implement the adapter. Create a class that implements the target interface and wraps an instance of the class with the incompatible interface. Use adapter pattern when you need to integrate a class with an incompatible interface into your system, such as using legacy code or third-party libraries. You're building a stock market app that processes stock data in XML. Now, you want to integrate a third-party analytics library, but it only supports JSON. Modifying the library isn't an option. You either don't have the source code or risk breaking existing features, so you need a smarter solution to bridge the data formats. To solve format incompatibility, you can use an adapter, an object that converts one interface into another. It wraps the original object and translates calls so two incompatible systems can work together without knowing about each other. In the stock market app, for example, an XML to JSON adapter can convert your data before passing it to the analytics library. This keeps your code clean and allows different systems to communicate seamlessly. Use the adapter class when you want to use some existing class, but its interface isn't compatible with the rest of your code. Use the pattern when you want to reuse several existing subclasses that lack some common functionality that can't be added to the superclass. 4. Decorator design pattern. The decorator pattern is a structural design pattern that allows you to add new behavior or responsibilities to an object dynamically at runtime without modifying its original class. Instead of creating lots of subclasses to add combinations of features, you wrap objects in decorator classes that add the desired behavior. Example, imagine you're ordering a coffee. You start with a base coffee, like espresso. Then you decorate it with milk, sugar, whipped cream, etc. Each add-on wraps the base coffee and enhances its cost and description. You don't need separate classes like milk espresso, sugar espresso, whipped milk espresso, etc. Just use decorators. Use decorator design pattern when you want to add behavior to individual objects without affecting other objects of the same class. When subclassing would lead to an explosion of classes. When you want flexible, reusable, and composable features. 5. Observer design pattern. Observer is a behavioral design pattern that lets you define a subscription mechanism to notify multiple objects about any events that happen to the object they're observing. One object, called the subject, maintains a list of dependents, called observers. When the subject changes its state, all registered observers are automatically notified. For example, Imagine you're subscribed to a YouTube channel. The YouTube channel is the subject. You, the subscriber, are the observer. When a new video is uploaded, the channel notifies all its subscribers. No need for you to ask every day, just wait for the notification. Use the observer pattern when you need to notify multiple objects about changes to a single object. You want to decouple the subject from its observers. Example, they don't know about each other's internal structure. Use the observer pattern when changes to the state of one object may require changing other objects, and the actual set of objects is unknown beforehand or changes dynamically. 6. State design pattern. State is a behavioral design pattern that lets an object alter its behavior when its internal state changes. It appears as if the object changed its class. Imagine a music player that has 3 states. Stopped, player is idle. Playing, music is playing. Paused, music is paused. Depending on the state, pressing the play or pause button does different things. If stopped, it starts playing. If playing, it pauses. If paused, it resumes playing. You don't change the player object, just the internal state, and its behavior changes. Use the state pattern when you want an object to change behavior dynamically at runtime, depending on its state. Use state when you have a lot of duplicate code across similar states and transitions of a condition-based state machine to eliminate complex if-else or switch statements based on state. Here an example. Context, the object whose behavior changes. Example, music player. State interface, common interface for all states. Concrete states, implement different behaviors, stopped state, playing state, pause state. Design patterns are proven, time-tested solutions to common software design problems. They are based on collective experience and represent best practices that have evolved over time. While the current list of design patterns is comprehensive, it's not exhaustive. New patterns may emerge as technology and programming paradigms evolve. As you work on more projects, you might even discover or create a pattern that addresses a unique challenge. And that wraps up our deep dive into design patterns. Mastering these concepts helps in making the code more modular, reusable, and maintainable. And they're often a highlight in technical interviews. If you found this video helpful, don't forget to like, share, and subscribe for more content on software development, interview tips, and embedded systems. Also, I encourage you to subscribe to my other channel. The links are in the description. Stay curious, keep learning, and see you in the next video.